Here, in the vast and intricate digital ecosystem, we find a remarkable tool, a master translator known as the compiler. It performs a task of profound importance, often hidden from view. A compiler is a special program that translates the language of humans into the language of machines. Programmers write instructions using languages like C, Java, Rust. But the computer understands only a primal language of numbers, ones and zeros. The compiler is the essential bridge between these worlds. Think of it as a meticulous artisan in a workshop. The programmer provides the raw materials, lines of source code, a detailed blueprint. The compiler takes this blueprint and begins a transformative process. It does not simply copy instructions, it deconstructs, analyzes, and rebuilds them. It checks for flaws, strengthens the design, and forges the final product. The finished article is an executable program. The compiler's journey begins with its first, most fundamental task, reading. Much like a scholar poring over an ancient text, it examines the source code character by character, but it does not yet seek meaning. Instead, it performs a process known as lexical analysis. Tokenization. The goal is to break the continuous stream of text into discrete, meaningful units called tokens. A token is the smallest building block of a language's grammar. Words like if, while, return operators like values like 10 and hello are all identified and categorized. Each piece is neatly separated, prepared for the next stage of analysis. This is like taking a sentence and identifying words and punctuation. For example, the lexer would not see one string of characters. With the code now broken into a stream of tokens, the compiler's next specialist, the parser, begins its work. The parser's objective is to determine if this sequence of tokens forms a grammatically valid statement. This is syntax analysis. It doesn't care yet what the code means, only whether its structure is correct. The parser takes the linear stream of tokens and tries to assemble a hierarchical structure, like diagramming an English sentence. Identify the subject, identify the verb, identify the object. That structure is usually an abstract syntax tree, the AST. The AST is the program's blueprint. Each node represents a construct in the code. Example, expression, a plus 5. The parser makes a tree with plus at the root child. Identifier, a, child, number, 5. The tree shows grammatical relationships explicitly. If tokens are in the wrong order, maybe a missing semicolon or a mismatched parenthesis, the parser halts and reports a syntax error. After a successful syntax tree, the compiler moves to semantic analysis. Once the compiler has successfully verified that the code is both syntactically correct and semantically meaningful, it can proceed to one of its most remarkable functions, optimization. The goal of the optimizer is to transform the program's structure to make it better, without changing its observable behavior. Better can mean many things. Faster execution speed, reduced memory consumption, lower energy usage. This is where the compiler truly shines, acting as an expert programmer that refines and polishes the code. The optimizer analyzes the abstract syntax tree or an intermediate representation derived from it, looking for opportunities to improve. A vast array of optimization techniques can be applied, ranging from the simple to the highly complex. One common technique is constant folding, where the compiler computes constant expressions at compile time. If the code contains 2 times 10, the optimizer replaces it with 20, saving the CPU from repeated multiplication. Another technique is dead code elimination. For example, code inside an if-false block can be removed entirely, shrinking the program and avoiding wasted cycles. The journey is nearing its end. All that remains is the final, definitive act of translation, code generation. This is the stage where the compiler converts the high-level, optimized intermediate representation into the low-level language of the target machine. This output is often machine code, the raw, binary instructions that the computer's central processing unit can execute directly. Each CPU architecture has its own unique instruction set. x86, ARM, another architecture. The code generator must be an expert in the specific dialect of the target it is compiling for. This process is intricate and highly technical. The code generator traverses the optimized abstract syntax tree or intermediate representation one last time. For each high-level construct, it emits a corresponding sequence of low-level machine instructions. An operation like a equals b plus c is broken down into fundamental steps. Load the value of b from memory into a CPU register. load the value of C into another register. Instruct the CPU's arithmetic unit to add the values in those two registers. Finally, store the result from the register back into the memory location for A. The code generator must also manage the use of the CPU's limited number of registers efficiently, a complex puzzle known as register allocation. This is critical for performance. In some ecosystems, the compiler does not generate machine code directly. Instead, it produces an intermediate language often called bytecode.